Thanks a lot. Thanks. Thanks for this extensive introduction. Is my voice strong enough for you to hear? Okay. So I think my talk is going to tie in quite well with Cor's talk. Cor focused on Benders himself. I'm trying to put Benders' result a little bit in the context of what was known at the time that Benders was working on his algorithm. And it's 100th birthday minus 1 day, if I understood Frits correctly. But I think it's a common agreement that this day works better than a Saturday. Okay, so you've seen Bender's day. So I'm basically just going to state it again, and I'm stating it not because I want to remind you of the details of the algorithm, but more I want to point out certain things that are important in the context of the history. So and people use x sometimes for the complicating variables, sometimes y, and so on. So this is to keep you alert, of course. But the thing is that we have a special set of variables that I call y that belongs to some set, and we don't. Benders did not put really any restrictions on it. He said that it's just an RQ dimensional vector, and of course, this function f, little f and capital F are also generic in the work of Benders. But we have some variables y that we put some emphasis on. That's important. And he concludes correctly that if you have a fixed y, so y bar, then you end up with a linear programming problem. So you have just a constant here, f of y bar, and here you have this vector that is constant. So you have an LP. And then you can rewrite this problem as an outer problem and a function here, phi of y. And this phi of y is simply like given y, you get this LP. And we can assume that this is a bounded problem. And then, as we heard already in the first talk, that if we use Farkas' lemma, then we know that this LP star here is feasible if and only if this holds, where U is sort of a dual vector. And in particular, it's the rays, the extreme rays of this dual set here. And if it is feasible, then we get this phi of y to be the minimum over all UK times this vector here, and the U1 up to UK are the extreme points of this dual space. So we have these extreme rays and we have the extreme points, and these are, of course, what form our Benders cuts. So we write this problem and we get this formulation that you have now familiarized yourself with during the day. And we have this dual set here, and where the tilde vectors are extreme rays, and in the U vectors, standard U vectors, are the extreme points of this dual space. Okay, so this is what Benders called his partitioning technique, and partitioning, of course, means that he partitions his variable set into some variables x that are nice LP variables, and some variables y that we don't make too many assumptions on. And what we nowadays refer to as the master problem is, of course, this one, but we don't solve this for all the extreme rays and all the extreme points, and that's, I think, where the name decomposition came in, that you generate these cuts as you need them. So you start with some number of constraints here, you solve the problem, and then you get a certain y out of the master problem for the limited number of cuts. And then you plug it into the subproblem, which is based on the dual. And then you can observe, of course, that in many cases this partitioning procedure by Benders is used if the set of y consists of the integer variables, but you have to, it's not that they disappear. If your starting problem was an IP and your y variables are IP, your master problem is still an IP. So that is important to remember. So this is just recapping Bender's decomposition. So after listening to the nice introduction, you might ask, what is my connection with Bender's? Well, I work with Cor, so they have an indirect connection. But actually, in my scientific infancy, I also worked on Bender's decomposition. When I was sort of transitioning between my master's and my PhD, I did some work on Bender's decomposition, and this was one of them. And here is another one. And here, even the name Bender's decomposition doesn't come in, but the term cross decomposition comes in, and cross decomposition is actually some kind of mixture of Danzig-Wolff and Bender's, where you sort of try to solve only the subproblems of the Danzig-Wolff and the Bender's decomposition, in the hope that they will give you something, because the Bender's master problem is heavy. If you now talking about the classical approach. But you try to solve them, and then once in a while you do a sort of a convergence check, and if it doesn't converge, then you go up and you solve the Bender's master problem to get things back on track again. So that's so Bender's decomposition is an important part of cross decomposition. So that's basically my experience. But I was sort of starting my PhD in the time that really new things happened in integer optimization, which probably had an important effect on what was done in terms of decomposition. And a remark is that if you read papers, it's often said that the Bender's decomposition was developed for solving mixed integer programs, but if you read Bender's paper, he mentioned it just as one of the possibilities. It's not developed for integer optimization. Actually, integer optimization hardly existed when Bender's was working. So if you read his paper, and I recommend you to do it, because when I listened to Cor and I've read the paper, it is a 100% match. If you read the paper, it's a very modest paper. He's very modest, very calm writing style, very to the point, very factual. It is absolutely no bragging in there. He's extremely, if you read it, I'm surprised how cutting edge he was, actually. I mean, he mentioned things that we talk about today as, oh, that's a smart thing to do, and he did it already in the 60s. So he says that he said Y is just an arbitrary subset of RQ, and he says an example is the mixed integer programming problem, and other examples are those in which certain variables occur in a nonlinear fashion. That's of course why you have these functions, more general functions, little f and capital F, because these could be nonlinear functions. And he could treat them as well. So in that sense, it's also said that, okay, it's the dual approach of Danzig-Wolff, which is true in the case of linear programming. But his method is more general than that. So he talks about Y in very general terms. Also, when he defines his algorithm, which he calls his computational procedure, he talks about Y generally. But then he has a section in application, and as Cor says, he was interested in modeling problems and solving problems. He says that the crucial point in the application of the procedure, blah, 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 is the existence of efficient procedures for solving the master problem. So he recognized that this is actually the bottleneck. And that is, of course, because you still need to deal with your variables Y. As a third application, he mentions a couple of applications. He says that as a third one, he says that Y is the set of all vectors in RQ with non-negative integral valued components. And then he says, okay, then you should use Gomery cutting planes. And then today you would say, oh, is that the right thing to do? But of course, this was what was known at that time. And then he also refers to the case where the integer variables are 0, 1. And then to deal with it, he says that he has his own combinatorial procedure together with co-authors Catchpole and Hurkens. And that is a procedure from 1959. Okay, so now we have to think about 1962. The paper is published in 1962, but as you know, when it's published, it's not done in that year. It's probably done a couple of years before. And in particular, he did this in his PhD thesis that was defended in 1960, which means that he probably did it in 59 or 58 or something like that. So we are talking that time period. But that is, of course, true for all the others that with a certain name or publication it's done before. But we are talking about really end 50s, beginning of 60s. And then you have to think about what did people know in terms of theory at that time. Well, they knew how to solve LPs, or at least they knew the theory of LP. They knew the theory of duality well, I would say. And also certain implementations were available of LPs. It was known how to solve pure integer programs, at least in theory, because Gomery's cutting planes, there are various working paper versions of this, but it's around 58, 60, so really at the time where he started to finish his thesis. So this is the integer form, or what we today call the Gomery fractional cuts. They were from that time period. And what about mixed integer programs? Well, that was really hardly known at all when he was active. So Biot, he had an algorithm that actually used Gomery's fractional cuts as a subroutine to make him able to solve mixed integer optimization problems. And then you had the Landon-Doig enumeration procedure, which is basically branching on hyperplanes but using only coordinates. So we are, before branch and bound, we are really enumerating now on coordinate values. And then Gomery, of course, worked on his mixed integer cuts. And if you read the Landon-Doig paper, then it says still unpublished, but they say that we know that this procedure exists. And then you have to think back also what Cor said, that this was not like, okay, you send an email and said, what's up, guy, and can you send me your latest working paper? No, you had to write a letter, and you even had to know first that it existed. So then you had to be maybe on a conference or know a colleague who knew someone. So it was a little bit longer lead times on getting access to the newest stuff. And of course, this was really at the same time, basically, the solving large LPs with block structure. That was the Danzig-Wolff decomposition procedure. So this was basically what was known in the field of, I'm probably forgetting someone, but roughly speaking, this is what was known when Benders was working. And it is also interesting to see that how people wrote in that time. If you read the paper now, you have long tables, you have, my algorithm outperforms everything that has been done in the history up to now, and so on. These guys were extremely pessimistic about their own results. So Landon-Doig says that it's not suggested that this method should supersede successful ad hoc methods for particular problems. In fact, it may in fact be chiefly useful for testing the validity of proposed ad hoc methods for new problems. So that was their claim to fame. Biot, he wrote a survey in 1964, so this is post-Benders, but he says, and the spelling, I don't know if this is spelling mistakes or if it's a British English or American English. So he says several computers codes using variants of one or both methods, and then he refers to Gomery's two methods, have been written and have successfully solved many real problems. Okay, that is fairly optimistic, but then he says, However, their performance has not been nearly as predictable as that of ordinary linear programming codes, which are themselves rather unpredictable as regards running time. The field of mixed integer programming is less far advanced. Gomery had extended his methods and various computer codes have been written using this method. Reports on their performance have varied from good to disappointing. So this is this is how they were bragging in the 60s. And of course, these guys had the first encounter with complexity, probably. That was what was happening. The concept was just not known yet. And then he writes, Driebeck and Dakin have developed programs using a branch and bound method for integer programming. So Dakin, he did the binary tree version of branch and so this was really in the infancy. And what was known in terms of computations, that's even more interesting because there are very few people who really knew how to do computations in that time and had the equipment to do computations. So Alan Hoffman, he had something called a SEAC computer, and they were able to do 10 constraints, 20 variables. So basically what you could do almost by hand. And then Orchard Hayes has played a very important role in computational optimization. And he and Danzig, they started a cooperation at RAND around 1952, and that continued for around 4 years. And they had something called the card programmable calculator. And Orchard Hayes is cited to say, one did not program in a modern sense, but wired 3 patch boards, which became like masses of spaghetti. And they could solve now 45 constraints and 70 variables. That was somewhere in that period that they worked together. And then you have various improvements. And at some point, Orchard Hayes went to something called CEIR. I don't know exactly. Maybe someone knows what that abbreviation is. It's in Virginia somewhere. I don't know. Maybe something military. Yeah. They made it possible to handle around 500 constraints by the end of the 50s. But these guys were really having the equipment and were fairly unique. That was not something that was generally available. And then if we go to MIP, and then you have to think about, well, Len and Doig came with their first approach in 60, and Dakin did the binary tree thing. Then there was a code called LP/90 that was developed by Orchard Hayes, who had now moved away from RAND, and it was sort of the first, and the successor, LP 1994, became the first code to handle MIPS due to the work by Beal. So this was after Benders. And Benders actually did some computational tests, and you have to think about, he did this in this context, and so he was a computing guy. And he said that the typical instance size, now I could only see one, so that was apparently the typical one, had 29 continuous and 27 integer 0-1 variables and 34 constraints. So that was sort of cutting edge at that point. And he had a computer for it sounds almost like a Ferrari, but it's a Ferranti computer. He used dual simplex, okay, so he implemented that. And then he said that you shouldn't add just 1 or 2 cuts per iteration, you should do more. And that was something that was later observed when you implemented Gomery cuts, that you shouldn't just do like the proof of Gomery's cutting plane, where when you do this convergence proof, you add 1 cut at a time. If you do that, it's not computationally very good. But you have to do more. And that was something that Benders also realized. And then he even sort of thinks about algorithm performance. So he says that, okay, the computational effort of his 0-1 approach that he did with Catchpole and Hurkens depends exponentially on the number of variables. So this procedure is only of limited use. So he observes that, okay, this algorithm has exponential running time, be careful. But then he also says that, okay, it works for up to 30, 40 variables with present computing equipment. And then he makes another interesting statement that this requirement is satisfied in many applications. Okay, so then he should probably go to Ortec or to KLM or to Picnic or something like that, and say that, okay, we are talking large scale here. But thinking in that context, he was really doing things that very few people could. So if you are more interested in the history of how mixed integer programming computation developed, then I recommend this paper here. It was in a special volume printed for the ISMP in Berlin, I think, and it has some nice chapters. Okay, so in the 60s and 80s, then suddenly a lot of work was done on computation, because that's basically what they had. I mean, you had to do something to make the problem easier to be able to handle it. So you can say that there are two main approaches: the dual or the price directive approach, which is, for instance, column generation, Danzig-Wolff decomposition. Then you have what Benders did, his partitioning procedure from 1962. Then you have something called Kornai-Liptak decomposition and Tenkate decomposition. This is nothing else than Benders, but with the certain structure of the constraints. Then you have this cross decomposition, as I referred to before, by Van Rooij in 1983, where you basically try to solve subproblems as long as you can until you see that the convergence is not happening. Then you need to go and solve one of the master problems, and if it's an integer problem, you have to solve the Benders master problem. And then, of course, Lagrange relaxation. We shouldn't forget that a lot of important stuff was done with Lagrange relaxation, and a very famous one is from Helden Karp for the TSP. And Joffrin did a lot of work on also the theoretical results related to Lagrange relaxation and subgradient optimization. So why didn't maybe things change? You see a change in the 1980s, and then it was a lot of things coming together in the 1980s, and a very one important thing that happened was that people started thinking about branch and bound and search strategies. If you read the old papers, it's basically depth first search, so last in, first out. And that can be good, and it can also not be good. And then they started thinking about it. And then it was many things happening together. Suddenly, very good systems came. So the first Cplex version came in 1988 with callback functions, these kind of things. And then Minto came in 1991, which is sort of skip kind of thing. It was open source. You could basically plug in. It was just a very general shell where you could plug in your own routines for cutting planes, for this and for that. And that was in 91. And then what also, of course, happened was that suddenly people started to have their own computers where they could actually sit and experiment, and these computers started to actually be able to do something. And you didn't need to have a big mainframe with cards and everything like that. And spaghetti. So there, and then of course the work of Karmakar, which was on interior point method, but people are competitive. So when things started moving with the interior point methods, also the classical simplex people started getting their gear, shift the gear, and it became very competitive, and this sparked a lot of developments in the simplex algorithm itself. And another thing that happened was that some people with strong characters, such as Manfred Padberg and Martin Grötschel, they started working on computations for TSP, and they used results from polyhedral combinatorics, which was a very sort of hot topic in the beginning of the 80s and through the 90s and so on. And got it really to work and beat records, solving the largest TSP instance and so on. This was continued by I mean, Grötschel and Padberg, Rinaldi, Junger, Reinhold, and later the whole group around Bixby, Applegate, Cook, Schwartau, and so on. It became really massive developments. And I mean, if you see what can be done now with the code of the Applegate, Bixby, Schwartau, and Cook group, they can solve instances of millions of cities up to 0.000% deviation from proven optimality. And of course, the spark for this work was partly the very impressive work of Danzig, Fulkerson, Johnson in 1954. So you see that sometimes things need a little time. But then, of course, it sounds like, okay, things went on until the 80s, and then it dropped dead, and I think I'm the third person who shows this figure in one form or the other, and we have all read this paper. And of course, I mean, this also has to be seen in the light that there are more scientists now than there were in 1960s. So there are more papers produced overall. So whatever, if you would do branch and bound, it will probably also look like that and so on. But of course, there are a lot of developments in decomposition, and then indeed it's in particular benders, I would say, because it's such a general framework. And this is because people notice that certain problems are actually quite nice to solve with benders, and also in the algorithm itself, many developments have been done. So I'm not going to, I mean, we have seen a lot of it, but I'm going to mention along some axis that these improvements have been done. I see my set Y has made a shift here, but that is an issue. Like with every decomposition method, you have to be careful how you decompose. If your subproblem becomes too trivial, it's solved very quickly, but it doesn't give you any useful information back. So you need to have some kind of quality balance in your decomposition, which is not so easy. So it might, as we have heard before, it might not be so trivial to say, okay, do the integer variable in y and the rest in x. I mean, you might have to be a bit more refined than that. And then in the solution procedure, the number of cuts can be really large, and that, I think, is what people struggle with sometimes. Should you then remove cuts, and which one should you remove that you avoid reiterating and generate them again? Should you solve the master problem to optimality in every iteration? Yes or no? What do you lose? What is necessary for convergence? Then you have this kind of, so if y is the set of integer variables, then of course you would solve basically each master problem by branch and bound, which is not so efficient. So there are developments in doing one branch and bound tree and instead of one for every time you solve the master problem. And then you have cross decomposition, avoid solving the master problem unless you must. Then the quality of the cuts. Often the subproblem has multiple solutions. How to find the best ones. That is, I think this line of work was sparked by Magnanti and Wong in the 80s. You can use Bender's decomposition in a heuristic fashion. There I've plead guilty in the sense of maybe relaxing cuts or certain cuts. But you can also solve the master problem heuristically if you are careful about convergence and so on. And then finally, you could improve or further develop the decomposition method itself. And we saw, for instance, the logic-based method is an example of that. So I think that was basically what I wanted to say. I think that is the end. Yes, it is the end. So I want to thank you for your attention. Mm-hmm.